Hello friends, in this lecture we will study the working of 1-bit memory cell. Before we will see the basics of the flip-flop or what is meant by flip-flop. As we know the basic difference between the combinational circuit and sequential circuit, the output of combinational circuit depends on only the present input and it doesn't depend on the past status of the input, so it has no memory. But the output of sequential circuit depends on present as well as past output. So to provide the past input or output, memory element is required. So for sequential circuit, flip-flops are used as a storing element. In this lecture, we will cover why flip-flop is called as a storing element. So basically the flip-flop is a sequential circuit which is used to store the digital information. So flip-flop is also known as the basic digital memory circuit. Now flip-flop has basically two stable states, that is logic 1 and logic 0 state. And we can design flip-flop by either NOR gates or NAND gate. As we know, the NOR gates and NAND gates are the universal gates. Now let's design the flip-flop by using two NAND gates. Now figure shows cross-coupled inverter. Now why this figure is called as a cross-coupled inverter? First of all, let's see what is meant by inverter. Now in this circuit, two NAND gates are used, that is NAND gate 1 and NAND gate 2. Now here both the NAND gates are acting as an inverter. As we know the working of NAND gate as a NOT gate, if suppose the same input is applied to the both the input terminals of NAND gate, then our NAND gate will behave as an NOT gate or inverter. That's why it is called as an inverter, because same input is applied to NAND gate 1 and NAND gate 2, that is A1 and A2. Now why cross coupled? Because the output of first NAND gate is applied as an input to the second NAND gate. Similarly, the output of second NAND gate is applied as an input to the first NAND gate. That's why this circuit is called as a cross coupled inverter. Now let's see its the working operation. Now case 1. Now to understand the working, we will divide the working in two cases. Suppose in case 1, assume that initially the output of gate 1 equals to 1. Now output of gate 1 equals to 1 means Q equals to 1. Now if suppose Q equals to 1, then A2 equals to 1. Now why A2 equals to 1? Because the output of NAND gate 1 is input to the NAND gate 2. That's why when Q equals to 1, then A2 equals to 1. Now when A2 equals to 1, then the output of gate 2, that is Q bar, which is equals to 0. Now this will make A1 equals to 0. Now again, why Q bar equals to 0? Because NAND gate 2 is working as an inverter. That's why as input to the NAND gate 2, that is A2, which is equals to 1, that's why the output of NAND gate 2, which is equals to 0, that is Q bar equals to 0. Now when Q bar equals to 0 means A1 equals to 0. Why A1 equals to 0? Because the output of second NAND gate is input to the first NAND gate. That's why A1 equals to 0. Means Q continues to be equals to 1. Now this will be our case 1 when Q equals to 1. Similarly, we will see the case number 2. If suppose Q equals to 0. Now if suppose Q equals to 0, then A2 equals to 0. If suppose A2 equals to 0, then the output of NAND gate 2, that is Q bar, which is equals to 1. Now this makes A1 equals to 1. Hence Q continues to be equals to 1. Now these are the two cases. If suppose Q equals to 1 and Q equals to 0. Now what is our conclusion? The outputs, that is Q and Q bar, will always be complementary. Now what is meant by complementary? As we have seen the working of the circuit, if suppose Q equals to 1, then Q bar equals to 0, and if suppose Q equals to 0, then Q bar equals to 1. Means the outputs, that is Q and Q bar, will always be complementary. That will be our first conclusion. Second conclusion, this circuit has two stable states. That is, first, one of them corresponds to when Q equals to 1 and Q bar equals to 0, then this state is called as logic 1 state, or this state is also called as a set state. Similarly, other corresponds to, if suppose q equals to 0 and q bar equals to 1, then this state is called as an logic 0 state or reset state. This will be our second conclusion. Now third conclusion, if the circuit is in set state, then it will be continued to be in set state. Similarly, if suppose the circuit is in reset state, then it will be continued to be in reset state. And this property of circuit shows it can store only one bit of digital information. That's why it is also called as a 1-bit memory cell. Thank you.